Okay, so in this problem, we're asked to find the pH of a 1.0 molar solution of HC2H3O2, and we're given the Ka value for this acid. So right off the bat, I'm going to notice a couple things. This is a weak acid. We can tell because it's simply not one of our 6 strongs, and also it has a Ka value. Strong acids don't have Ka values because they would be infinity. They proceed all the way to the right, so they don't have Ka values. So we've got to think, if this were just a strong acid, so Sa for strong, that would fully dissociate. I don't like Sa, let's change that. Let's call it Ha, but we're going to pretend it's a strong acid. It's going to fully dissociate into hydrogen ions and whatever anion you've got. So if this were a 1.0 molar strong acid, for every one Ha, you'd have one H dissociating off, so the concentration of your H plus ions would be 1.0 molar, just like the concentration of the strong acid. Then you would simply take the negative log of this to find the pH, because pH equals negative log of the H plus, or you could write H3O plus there, they're interchangeable, and that'd be an easy problem to solve. The problem we have, though, is that this isn't a strong acid, so it's not going to fully dissociate. So we've got to do a little bit of thinking about how much of it will dissociate, and then we might have to solve for that. So let's write an equation here. We've got our HC2H3O2, which is aqueous, reacting with water, which is a liquid. We know it's going to establish an equilibrium because it's a weak acid. This H here on the front of this is actually acetic acid. That H is going to be donated, so it'll become H3O plus, AQ. There's your acidic component, or the part that we'll use to measure the pH anyway. And the anion, C2H3O2 minus, I'm out of room, I really should put AQ behind that, but I don't have any more space. So think about what we know here. We know some initial concentrations, we know something's going to change, and we know an equilibrium is going to get established. Well, initially we have 1.0 molar of this weak acid. I don't really care about water because it's not part of the equilibrium expression. And then over here I have no H3O plus, nor do I have any of the anion because the reaction hasn't begun yet. So start thinking about the changes here. You know some of this is going to leave because some of it is going to dissociate. So that's going to wind up giving us an equilibrium concentration of the HC2H3O2 of 1 minus X. Now, bear in mind, though, that this X, this amount that's dissociating, has to be a pretty tiny number because your Ka value is 1.8 times 10 to the negative fifth. That means hardly any of this reaction is going to progress to the right. Most of the reactants are going to stay unreacted. So this X here is going to be tiny. So if we continue that thinking, though, again, we don't really care about water. That's fine. But over here on the H3O plus, initially we had none of it. Now we're gaining that same X, that same small amount of H3O plus, and we're also going to gain the same amount of this anion because it's a 1 to 1 to 1 ratio of all of these. So that's going to leave us with an equilibrium concentration of H3O plus of X and an equilibrium concentration of X for the C2H3O2 minus. Now, if you were to set up an equilibrium expression for this, it would look something like Ka equals X times X over 1 minus X. Now, we do actually know a Ka value, and we know, actually that's all we know, so we could try to solve for X here. The problem is when you go to do that, you're going to have to incorporate the quadratic formula because of this horrible 1 minus X down here in the bottom. Luckily, on the AP exam and on any of my tests, you are never going to have to use the quadratic formula. Instead, we're going to make an assumption about this part of our ice chart right here. So we are going to make the assumption that this X is so little in comparison to this 1 molar that it's basically not going to change. It's like having $1 trillion and losing 10 of them. You still have $1 trillion for all you care. So in order to make that assumption, you actually have to state it. It is assumed that the change in the concentration of HC2H3O2 is negligible. What that means is we're going to then make the assumption, instead of it being 1 minus x, it's essentially still 1. If you do not state this assumption here, though, you can't use what's about to happen. So now, instead of our equilibrium expression looking like this monstrous thing right here, what winds up happening is this denominator simply is this concentration, which remained unchanged, and it's 1. So we now have a problem that's significantly easier to solve. Ka equals x times x over 1. Well, we can simplify that down. X times x is x squared, and nobody cares about dividing by 1. So now we simply just plug in the value for Ka, which is 1.8 times 10 to the negative 5th. So 1.8 times 10 to the negative 5th equals x squared. In order to solve for x, we'll square root both sides. And that winds up with an x value of 4.24 times 10 to the negative 3rd. So now we need to think about what we just solved for, though. We solved for x, which in our scenario from the beginning here, x was the ever-important hydronium concentration. So two things. Since this is a concentration, we're going to give it units of molarity, so 4.24 times 10 to the negative 3rd molar. And then we need to actually remember we're trying to find the pH. So in order to find the pH, you're simply going to take the negative log of the H3O plus concentration, which in this case we just said was 4.24 times 10 to the negative 3rd. So we'll take the negative log of that, and we find that the pH is 2.37, which makes sense. It is an acid, so it should have an acidic pH somewhere less than 7, but it's not going to be a ridiculously low pH because it's not a ridiculously strong acid. It's in fact a weak acid.